start the recording. All right. We'll give people about 30 more seconds, then we'll get started. It'll probably just be the five of us, maybe one or two more. I should go get a drink of water. All right, so let's start talking some good old bit more Gauss's law and some applications and also potential energy. So, main thing, you guys have been using Gauss's law for, like last week or two now. So what exactly is Gauss's law again? Because you guys will still be using it. Gauss's law is what?
Integral E dot dA equals Q enclosed over epsilon.
Yep, exactly. So integral E dot dA is equal to Q enclosed over epsilon naught, and we use that to find electric fields for what kind of systems? What kind of examples? We're able to use Gauss's law to find electric fields for symmetric systems. Of course, you guys have been doing this for like the last week and a half now, so you should be relatively comfortable with it. So, now one more thing. We know what's the main difference between a conductor and an insulator? So what exactly is a conductor and what significance does it have in this class specifically?
For conductors, charges are stored on the outer shells.
Yep, and so what does that mean about what goes on inside a conductor?
The electric field is zero.
Exactly. So that's the main thing we need to know is for a conductor, the electric field inside is equal to zero, and like you said, the charges essentially get moved to the outside of the conductor, or like to the edges of the conductor in such a way that the electric field is zero. So, and then an insulator is just charges, or however they're usually going to be like uniformly spread out, at least in this class. So that's pretty much it in terms of Gauss's law. And then what is electric potential energy? Like, anyone want to give me a quick rundown of what electric potential energy is? What is electric potential energy? Go ahead, Harsha.
For the equation is KQ1 Q2 over R.
Mm-hmm. And so what exactly does that mean?
So like in mechanics or like physics 121, potential energy was used to like measure like resting objects, or how much energy like a an object that wasn't in motion like used to measure that. So like for like charges, like you can use electric potential energy to find out like how much potential energy there is between two charges.
Exactly. So basically, you can use it to sort of quantify how much potential energy a charge can have at a certain point. Like the same way if you hold an apple, in your hand, and let's say it's a meter above the ground, it has a certain amount of gravitational potential energy, where if you let go of it, it's going to end up falling downwards and gaining kinetic energy. Sort of the same way with charges with electric forces. So let's go ahead and hop into an example. And if there's anyone that hasn't already, if you could put your campus IDs in the attendance form that's posted in the announcements, that would be greatly appreciated. So let's go ahead and take a look at a, sort of a beginning of a Gauss's law example, and we're just sort of going to build off this example for this session. So we have a uniform insulating sphere of charge with radius A. So let me go ahead and sort of visualize. We're going to have a sphere of charge here with radius A is uniformly charged with a charge density rho, plus 400 microcoulombs per meter cubed. I don't really care about the numbers too much, but it's useful to have them because then we can plug in at the end and actually calculate stuff. But I'm just going to leave it in terms of rho, A, B, C, etc. So we have this sphere charge, and it's going to be surrounded by a conducting shell with an inner radius B and an outer radius C. And the shell is uncharged. So first of all, we want to know what's going to be the total charge on our inner sphere of charge, and then what's going to be the magnitude of the electric field at all of these different locations. So let's say I'll give you 10 minutes, then we'll go talking through this. If you have any questions, feel free to ask. Yeah, whatever. I can't get it to fill in on the inside. All right. So we have our insulating sphere of charge at the center. We have its radius and we have its charge density. And we want to go ahead, first of all, what's going to be the total charge on our inner sphere of charge? What's our total charge Q? So we're given the charge density and we're given the radius. How do we get from the charge density to the total charge?
You do rho times volume.
Yep. So we have our charge density rho times the volume, and the volume of our sphere is what? What's the formula for the volume of the sphere?
4/3 pi r cubed.
Yep, exactly. 4/3 pi r cubed. In this case, r is a, so it's 4/3 rho pi a cubed, which we were to go ahead and plug in the numbers. Did anyone get a value for this? Let me pull up a calculator. So we have 400 microcoulombs per meter cubed. So that's a 10 to the minus 6. Keep everything in SI units. Times 4/3 times pi times A is 5 centimeters, 0.05 meters cubed. You get a total charge of about 2.1 times 10 to the -7 coulombs, or about 0.2 microcoulombs. So now we have our total charge on an aerosphere charge. So we want to know what's going to be the magnitude of the electric field at these 4 locations. And if you actually went ahead and did quick Pythagorean math, you'd notice that each of these 4 is within one of 4 different regions here. So the first point, 1.52, where is that? Is that between our sphere and our conductor, or is it inside our sphere?
It's gonna be inside our sphere.
Yep, inside our sphere. So how do we actually find the magnitude of the electric field inside our sphere? How do we use Gauss's law to find our magnitude of our electric field inside our sphere? So let's say at like a radius like that.
Can't we draw like a Gaussian sphere and then find the enclosed charge?
Exactly. So if we go ahead and draw our Gaussian sphere here, let's say it has a radius r, and we'll plug in our value for r at the end. What's going to be the total enclosed charge?
Just rho times the volume of the Gaussian sphere.
Yep, so it's rho times 4/3 pi r cubed, r being, whatever 1.5 and 2 the hypotenuse of that comes out to be. So Q enclosed is 4/3 rho pi r cubed, and our integral for E dot dA ends up becoming what? How do we simplify our E dot dA integral?
It becomes just EA.
Yeah, exactly. It becomes E times the A. A is area of what?
Of the Gaussian sphere.
Yep. And so what would that area be? We know the volume of our sphere is 4/3 pi r cubed.
This area would be 4 pi r squared.
Exactly, 4 pi r squared. 4 pi r squared. So E times our area is equal to our Q enclosed over epsilon naught. Right? And we can solve for our electric field by dividing our 4 pi r squared over. So the 4 actually cancels out, the pi cancels out, r squared cancels out with r squared, so we have 1r on the top. We know we have epsilon naught on the bottom. We also have a 3 on the bottom, and we have a rho. So we have rho r over 3 epsilon naught. So essentially, our electric field increases linearly inside the insulating sphere, which then we go ahead and plug values in. We have r would be 0.015 squared plus 0.02 squared, and the square root of that is about 2.5 centimeters. Actually, exactly 2.5 centimeters. We multiply that by our rho, our charge density, 400 times 10 to the minus 6, over 3 times epsilon naught. What's the value for epsilon naught? Hint, it's in your formula sheet.
10 to the negative 12.
Yep, exactly. 8.85 times 10 to the minus 12. We plug it all in, and we get an electric field of about 3.8 times 10 to the 5. And what's the SI units for electric field?
Newtons per coulomb?
Yep. Newtons per coulomb. Or does anyone know another way we can put our electric field? Newtons per coulomb is the main one, but there's another way we can use volts.
Yeah, volts per meter, right?
Yep, exactly, volts per meter. But I'll just leave it as newtons per coulomb. So now, part C, so we found our electric field inside our sphere of charge. Now we want to go ahead and find it at a radius of 7 centimeters, which is obviously between our sphere of charge and our conducting shell. So it's, like somewhere right here. So we're going to once again draw a Gaussian surface. What's our total enclosed charge?
It's the Q we found in part A.
Yep, exactly. It's just the whole Q of our sphere of charge. So Q enclosed is equal to big Q. And then, so what would be the electric field here? How do we find the electric field?
We could do the same thing, right? And then make a Gaussian sphere
Mm-hmm.
using that as our Q enclosed.
Yep, exactly. So we could do the same thing with Gaussian sphere. We have our Q enclosed as Q, E times 4 pi r squared, divide the 4 pi r squared, and we end up getting what? We get our 4 pi r squared divides over. So we are going to have our epsilon naught. We'll have a 1 over 4 pi epsilon naught in there. And we have our Q enclosed, which I'll just leave as Q. And our r squared, 1 over r squared. So our electric field is going to be 1 over 4 pi epsilon naught, big Q over r squared. What does that look like? Is r always the distance away from the center? Yeah. So anytime I write r up here, it means it's the distance from the very center to wherever we're working. So here, this is r. In part B, this was r. And yeah, so r is just the distance from the center. Yep. And this 1 over 4 pi epsilon naught, big Q over r squared. That just looks like a point charge, right? Point charge is kq over r squared, and k is 1 over 4 pi epsilon naught. And if we go ahead and actually calculate the value, plug in the values, we have 2.1 times 10 to the negative 7 times 1 over 4 pi epsilon naught. That's just k, so I'll just use 9 times 10 to the 9 over r squared. R is 7 centimeters. We get an electric field value of about 3.9 times 10 to the 5 newtons per coulomb. Part D. Quick, someone tell me what's the electric field for part D?
Zero.
And why?
Because it's within the conducting shell.
Exactly.
The Gaussian sphere is within the conducting shell.
Yep, exactly. So for part D, we're at we're at 0, 9 centimeters, which means we're right up here, and we are inside our conductor, which means electric field is 0. Boom, free points. Conductor. All right, and now what about part E? We want to find the magnitude of our electric field at negative 12.9. So we're like somewhere like out here or something. What's going to be our electric field out there? So we're outside our conductor. Does being outside the conductor mean the electric field is 0?
It's not gonna be 0, but you can find it the same way by finding Q enclosed, where Q enclosed is just gonna be the insulating sphere of charge, since the conducting shell is uncharged.
Exactly. So once again, Gauss's law, we find what our Q enclosed is. It's just big Q, and it's the same thing as part C. It's equal to 1 over 4 pi epsilon naught Q over R squared. In this case, R is going to be, we have it's what? Negative 12.9. So R would be the square root of 12 squared plus 9 squared, which comes out to be 15 centimeters out. And so we have K times Q, K 9 times 10 to the 9, and then Q is 10 to the negative 7, so it comes out to 10 to the 2. We're dividing that by 15 centimeters, which is 0.15 squared. We get an electric field magnitude of about 8.4 times 10 to the 4 newtons per coulomb. Cool, makes sense? Nice and easy, just nice and easy Gauss's law conductor example. Anyone have any questions about this so far? All right. So now let's go ahead and hop into the next part. Remember, our electric field inside the conductor is 0. Now we want to know how that's actually the case. So I want to go ahead and find our total charge on the inner edge of our conducting shell, so along here, and also along our outer edge out here, as well as then also get the surface charge density. We'll take 5 minutes and we'll go over this. If you have any questions, feel free to ask. All right. So we want to go ahead and find our total charge on our inner and outer edges of our conducting shell, and then also find our charge densities. So what's going to be the total charge on our inner edge of our conducting shell, and how do we find it? We have our total charge plus Q in here, and we know our electric field in our conductor is 0.
So Q inner is just gonna be the opposite sign of what we had for Q of the inner sphere,
And why is that?
because it needs to cancel out with each other and have the total charge within that be 0.
Exactly. So we have, if we go ahead and draw a Gaussian surface inside our conductor all the way around, we know that our total enclosed charge has to be 0 so that the electric field is 0. So that means if there's plus Q here, there has to be a minus Q on the inner edge. So part of has to be minus Q, which is negative 2.1 times 10 to the minus 7 coulombs. Has to be equal to the charge on the inside and opposite inside. So it cancels out, Q enclosed equals 0. And so what does that mean about the charge on the outer edge of our conductor?
Overall, the conductor has no charge, so the outer part of the shell would have to be the same in magnitude but opposite in sign of the inner charge.
Exactly. Plus Q. So we have minus Q on the inner part of the conductor and plus Q on the outer part. So now how do we get the surface charge density of our conductor? We have our total charges. How do we go from total charge to charge density?
We can just take the total charge and divide it by the area, which would be 4 pi r squared.
Exactly. So for H, we take our total charge, which is minus Q, divided by the surface area, which is 4 pi r squared. Our radius r is b, so negative Q divided by 4 pi b squared. Plug in values. B is 8 centimeters. So we have minus 2.1, 10 to the minus 7, divided by 4 pi times 8 centimeters squared. The charge density of negative 2.6 times 10 to the minus 6 coulombs, or negative 2.6 microcoulombs per meter squared, cubed, just per meter. What is it?
A meter squared?
Yep, exactly. It's an area, so meters squared. And so then for our surface charge density on the outside, we once again take our charge, divide it by the area. So it's going to be plus Q divided by 4 pi times the radius of the outside, which is C. C is 10 centimeters. So it's plus 2.1 divided by for pi 0.1 squared with a surface charge density of about plus 1.7 microcoulombs per meter squared. Yeah, that's the charge. Yeah, surface charge density is the charge per unit area on the surface. Any other questions? Does that make sense? Radio. So that's basically all you guys need to know for, like, you'll see a whole bunch of other examples with Gauss's law and seeing symmetry and having conducting shells surrounding things. It's all the same process where you know your inner charge inside a conductor, draw a Gaussian surface, and you know that Q enclosed has to be 0. And it's the same process for conductors with cylinders as well as spheres, and then also planes if you have infinite sheets of charge. So now let's go ahead and take a look at electric potential energy. So we're going to go ahead and have an electron that's going to start out at a radius of 15 centimeters. It's going to start out here. Actually, go ahead and move this over. Perfect. So we're going to have our electron start somewhere out here, and it's going to move in a straight line this way. So it's going to start at a radius of 15 centimeters and move in a straight line to a radius of 5 centimeters. So we want to know, one, how much work is going to be done on the electron, and two, if the electron is going to start at rest, how fast is it going to be traveling at 5, 0? So let's go ahead and take about 5-6 minutes, then we'll go over it. Actually, make this blue. All right, so we have our electron. It's starting out here and it's moving this way in a straight line, and we want to know how much work is being done on the electron while it does that. So first of all, how do we find work? Work is going to be equal to what?
It'll be the negative change in the electric potential energy.
Yep, exactly. So work is going to be the negative change in our electric potential energy. So is it as simple as just So what is our electric potential energy out here initially? What's our initial starting electric potential energy?
That'll also be okay, Q1, which would be like the electron charge, times Q2, which would be the basically just the inner sphere, sorry, divided by the radius.
Yeah, exactly. So we know that according to Gauss's law, if we're outside a spherically symmetric charge distribution, we can treat it as a point charge. And so we can treat this as just our point charge Q and use our U of R for 2 point charges to calculate our initial potential energy. So U naught is equal to K, we'll say this is QE, which is our electron, we'll just leave it as little q, times our big Q of our charge distribution over our radius R, which if we go ahead and plug values in, 9 times 10 to the 9, what's the charge for an electron? What's the charge of an electron in coulombs?
1.6 times 10 to the negative 19th coulomb.
Yep. 1.6 times 10 to the minus 19. And let's see. It's negative 1.6 times 10 to the minus 19. Divided by our distance r, which is 15 centimeters, 0.15 meters. We get an initial potential energy of something very small. So negative 2 times 10 to the negative 15. And what's our SI units for potential energy?
Joules?
Yep, it's just joules. So very small potential energy. And so what is our final potential energy when we're at radius of 5 centimeters? Well, it would just be the same thing, except instead of divided by 15, it'd just be dividing by 5, right? So is that just our work is just that total change in potential energy?
I think that's right, because there's no non-conservative forces working on or acting on it.
It's true, there are no non-conservative forces, but there is an area where there's no force acting, right?
Oh.
So we can go ahead and calculate our final potential energy, which is, whatever, negative 6 times 10 to the minus 15. But, we know that that's not, there is a part where there is no force acting. So if we keep that in mind, because remember, as we pass through the conductor, there's no electric field, so there's no force acting on the electron. So how do we go ahead and calculate our total work being done? Or how much work is being done while we're inside the conductor?
No work is being done while it's passing through the conductor, right?
Yeah,
So we would
exactly.
We'd have to subtract that amount out.
Yep, so we'll split it up into 3 parts. We'll say for the work in the section as it passes through the conductor, so WC is equal to 0, because work is a force times a distance, and there's no force, so there's no work. So we're going to have to split this up into essentially three separate parts, right? We want to go ahead and find the total work done on the electron from here to here. And we'll call it work 1. And then we have our total work being done from here to here. We'll call that work 2. We go ahead and calculate both of those and just add them together. And the part in the middle, where there's no electric field, there's just no work being done, and the electron would just move at a constant velocity. So, how do we get our initial work being done? We have our initial potential energy.
And then we also find the potential energy at the outer surface, right?
Yep, exactly. So we'll call it right here U1. So we have U naught, and then we U1. It's once again it's just K times Q times big Q over our radius R, which is 10 centimeters. So we go ahead and log that in, divided by 0.1. We get 3 times 10 to the minus 15 joules. Obviously, negative 3 times 10 to the negative 15 joules. And so our total work 1 is going to be negative times the change. So it's going to be, what, just 10 to the minus 15 joules, right? Does that make sense? So we would go ahead and subtract these. So we see we're decreasing. I'm using, like air quotes, decreasing our potential energy because it's increasing in a negative direction. And so then the change in that obviously is negative. So negative change is positive. It's 1 times 10 to the minus 15 joules. So then we go ahead and take a look at the second part. We'll calculate, let's say, U2 and U3. And go ahead and throw a little separator here. So U2 is historic band, and also, what's the radius here? If we start at the initial spot, it's the same enclosed charge, right? Gauss's law, the enclosed charge is the inner sphere. Our radius that we start at is 8 centimeters. So we just divide it by 0.08. And so we get a potential energy of about negative 3.8 times 10 to the minus 15 joules. Then U3, we finally end at a radius of 5 divided by 0.05. So once again, it's about negative 6 times 10 to the minus 15 joules. And so then from these two, we know that W2 is going to be go ahead and add this here. We get about 2.2 or 2.3. About 2.3 times 10 to the minus 15 joules. So then our total work done, work net, we literally just add those two together for the two separate parts, and we get about 3.3 times 10 to the minus 15 joules of work being done on the electron. Does that make sense? Anyone have any questions?
Wouldn't it be negative since, or
would it be a negative amount of work?
Yeah, because since it's the electric force would be pointing away since it's an electron and a negative. Oh wait, never mind. No, it's not.
You caught yourself there, right?
Yeah.
It's an electron, which means it's attracted to the positive charge.
Yeah.
So, yeah, so Harsha brought up a good point. If this were a positive charge here moving inward, it would be a negative work because we would be going against the direction it would want to travel. But in this case, our electron wants to travel towards the positive charge. So it's a positive work. That should at least that makes intuitive sense for me. That's one of the few things where I actually rely on intuition in this class. Or you can just calculate your potential energies and actually find the change in potential energy and then throw a negative sign in front of it. So we get our total work done. And so now, if our electron starts at rest, how fast is it going to be traveling once it reaches its endpoint? How do we find that? How do we get from work to velocity?
We could use our change in total energy equation, right?
Our change in total energy, so our delta E is equal to delta K plus delta U.
Yeah.
We could do that. But we know that delta U, our total delta U, is equal to our work being done. And what is our total change in energy, delta E?
0.
Yep, exactly. Our total change in energy, delta E, is equal to delta K, our change in kinetic energy, plus delta U, which we know is delta K minus our work. And we know that has to equal 0. Our total energy change is 0. So then delta K is equal to the work done on the electron. The work is the change in kinetic energy. You guys might remember that from Physics 121. So now, how do we relate our change in kinetic energy to our change in velocity? Or what is kinetic energy again?
mv squared.
Yep, exactly. 1/2 mv squared. So then we know our change in kinetic energy is going to be 1/2 m delta v squared. And our delta v, well, we start at 0 and we want to find our ending velocity. So we know this is just our v final squared, 1/2 mv final squared. And so then we solve for our v final is equal to 2 times the work divided by the mass. Take the square root and we get a value of, let's see, 6.6, 3.3 times 2, 10 to the minus 15, divided by the mass of our electron. What is the mass of our electron?
I have 9.1 times 10 to the minus 31.
Yep, exactly. About 9.1 times 10 to the minus 31. throw the 10 to the minus 31, just become positive and throw it on top. And then we take the square root of that, and we get our total final velocity. So it's about 8.5 times 10 to the 7 meters per second. That is absurdly fast, and almost to the point where we might have to start taking relativistic effects into account. But not quite. Anyone have any questions about this? I see Roberto's been typing. So for the homework for circular problems, we use Q over 2 pi r epsilon naught. Why is it different from what we did the first half? You mean for finding electric potential energy? Or I'm going to take a guess you are thinking about a cylindrical problem, right? Yeah, 2 pi r epsilon naught is, well, what's the electric field for cylindrical charge distribution? It's not Q, it's lambda, the charge density, over 2 pi r epsilon naught. Yeah, you got it figured out. Anyone have any other questions about this? So, we were able to use Gauss's law to first find our electric field at different points inside the charge distribution, between it and the shell, inside the shell, and outside the shell. And then we found the total charge on the edges of our shell, as well as the charge densities, using, once again, Gauss's law. And then we were able to go ahead and use electric potential energy to calculate the work being done on a charge that's moving around inside our electric field. Pretty straightforward. Hopefully this helped you guys out a little bit. You guys have your quiz tomorrow. Electric potential energy is probably going to be the main focus, because you guys started doing Gauss's law last week, and last week's quiz was more focused on Gauss's law. If you guys have any questions, feel free to put them in the homework chat or the class questions chat, because people are always hopping in there helping out. Thanks guys for coming to the session. Good luck on your quizzes tomorrow. Have a good day, everyone.
Thanks, man. You too.